Okay guys, I'm sorry that took so long to set up. Just these cables were not cooperating. No, so today we're going to begin our look at compression and some compression algorithms. Compression algorithms is probably the non-sexy name for this module. We're going to look a lot at compression. Okay? So, here's a useful definition of compression here. Compression is a reversible conversion of data to a format that requires fewer bits. And it's usually performed so that the data can be transmitted or stored more efficiently. Conceptually, it's often easier to imagine a transmitter sending something to a receiver rather than the storage mechanism being the medium in between. But it amounts to the same thing. Whether you're transmitting or just storing, it's sent and it's received. So, imagine that the post office didn't charge for letters by weight. Imagine they charged by size, by area. So imagine if it cost €2.56 to send an envelope this size. Okay? So if you put this into an envelope and posted it, it would cost $2.56. However, if you folded it in half and put it in an envelope that was half the size, it would only cost you $1.28. You could fold it in half even smaller. That would only cost you 64 cents. Or you could fold it in half again. Only cost you 32 cents. You're wondering how he's doing all that math in his head so quickly, but I chose the numbers well at the start. You could fold it in half again, maybe you got like a super tiny envelope. It only cost you like 16 cents to send. Now, of course, a letter in this form, in this tiny envelope, isn't very useful. Like, you can't read it when it's all folded up. So in order to use it, you'd have to, at the receiving end, unfold it again. Then you could actually read it. So compression is like folding up the letter. And then we have decompression, which is unfolding it so you can use it. And we generally talk about two kinds of compression: lossless and lossy. If what you started with and what you get at the end is a perfect copy, so if the thing that's received is a perfect copy of the original, then the compression was lossless. But if it's not quite perfect, it's lossy. Now, depending on the circumstances, a degree of loss may be acceptable. In some cases, it's not acceptable. So, if you went into Waterstones to buy a book, and they said, well, the book costs €22, but there's a cheaper version of it here that's only €5, but like every 20th word is just random. You might say, well, that's no good to me. Random words appearing in a book, that's not an acceptable degree of loss. I mean, if it was if you were on your holidays and you had massive roaming charges and it could cost you €5 to post to your Facebook page a super perfect picture of you, out partying, or you could get a quite good picture for 50 cents. You might say, I just send the quite good one. It doesn't have to be perfect. Similarly, if you got someone's wedding photos, and you folded them up, and you said, look, I saved you so much on postage. Here's your wedding picture. They probably wouldn't be happy. If they took a scan of your brain and there was some expert in Sydney who could, tell you exactly what was wrong with you and whether you were going to live or die and what they should do. And they said, well, it would cost now €80 to send that file to Sydney, but you could send it cheaper for €8. Now, it wouldn't be quite as good, like, well, in that situation, you might say, no, take my money. So even though it's the same trade-off between, a picture of you in the partying, your Facebook page, or, it's still the same trade-off. Depending on the circumstances, a degree of loss might or might not be acceptable. So anyway, we have compression, where we fold it up. We send it nice and small, and then when it gets to the other end, we have decompression. Okay? The first kind of compression we're going to look at is very simple. It's called run length encoding. And with run length encoding, what you do is you replace multiple occurrences of something with that thing and the number of times it occurs. So sometimes, for example, in phone numbers, we might say, it's 8555129. Now, I think saying 555 probably isn't a whole lot shorter than saying 555. But if you had a bunch of numbers where a lot of the time the same number came up, you might say, okay, there's 10 sevens, 2 1s, a 4, a 3, 9 6s. I think the most common real-life example is if you're in the checkout in Tesco and you have 20 cans of obviously posh cider, not any of the cheap stuff, that posh Swedish cider. Okay, you have 20 cans of cider. The person at the checkout doesn't go, beep, 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 beep. They have a look at how many you have, count them up, and you ever notice they kind of do, ding, 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 ding on the keypad, beep once, and then throw them all down the end to the bagging section. So that's a kind of run length encoding. If we look at this example here, instead of going A, B, 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 A, we say like 5A, 10B, 5A, 20K, 5A, and 10D. So that's much shorter than spelling it out. And that brings us to our first major point when it comes to looking at compression. Some kinds of data lend themselves to certain kinds of compression. I mean, it's not like all the data in the world is lined up nice and neatly like that, waiting to be just, mown down using run length encoding. It's not like everyone in Tesco buys 10, 20 and 30 of the same thing and lines them up all neatly on the conveyor belt. But sometimes the data might have these kind of properties, and if the data does have long runs, we call them, if it has runs in it, then run length encoding might be a way to save some space. So can we all agree that it's definitely shorter? But of course the opportunities to use something like that might be limited. There's a slight chance, you might get an image that would have a bunch of pixels all lined up like that. And so you could maybe say, we've got blue 4 times, red 15 times, that green 20 times, and then that blue 1 time. So that can happen in an image from time to time. Can you think of what kind of images it might happen in? Depend what's in it though. So what kind of images would tend to have big expanses of the same color all lined up in a row like that?
Screenshots are of course what we're looking at.
Well, you could have, what you're looking at here, for example, there's big expanses of white there. So if you were doing this pixel by pixel, instead of going like, white, 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 you might be able to say there's, 3,000 white pixels. And then when we hit the top of the or there, we might encounter our first black pixel there. So, you know, graphics, logos tend to be like that. Cartoons, you know, I mean, Homer Simpson's face is all the same color. There isn't much variation there. So in cartoons, we might see that kind of thing happen. So there's some kinds of image data where that can happen. Fax machines use something like run-length encoding. Okay, so run-length encoding replaces multiple occurrences of an item with the item followed by the number of times it appears, but that's only useful where runs in the data are likely to occur. So if you were to take a picture out the window there, you know, all those trees and all that grass and all those, you know, shiny, happy people outside, you probably wouldn't find there's many situations where you could use run-length encoding. You know, the chance of one blade of grass being the exact same shade of green as the other, and there being no shadows and things like that, you know, slim enough. Relative encoding is another kind of compression. And with relative encoding, we have a number of pieces of data, and instead of coding the absolute value of each piece of data, we code the difference between each piece and the piece that came before it. So here we have a bunch of values. We've got 512, 514, 518, 517, 510, 508. And what we do is we say, well, it starts with 512. Take that 512 then and do plus 2, which will give you 514. Then do plus 4, and you get 518. Do minus 1, and you get 517. Do minus 7, you'll get 510. Do minus 2, you'll get 508. Do plus 3, you'll get 511. And so on like that. And so there may be occasions when the data lends itself to something like that. So here, there are small variations from one piece of data to the next. And provided the maximum variation from one to the next is small enough, you can save a lot of bits coding it this way. If it was completely random, if they were just like numbers between 0 and 1024, and they were completely random, or let's say it was numbers between, I don't know, let's say it was between 0 and 256, right? Under normal circumstances, we'd need 8 bits to represent each possible value, because there's 256 of them. If it was just random numbers between 0 and 255, well, like, it would still take 8 bits. There's nothing you could do about that. But if we knew, for example, that between one value and the next, it was only ever like plus or minus 8, well then, plus or minus 8, you're talking about 16. We could probably represent each one in only 4 bits. But we'd have to have that constraint where it could only go up or down by minus 8 any one time. So again, there may be situations where the data is organized like that. That's only certain kinds of data. Anybody want to speculate? Has anybody seen any data kind of like this in the past? Well, if you look at the waveform for an audio file, for example, the waves, you know, there's a huge range of values, but it doesn't go from one and then to another random one and then another random one. It gradually gets where it's going So the variation between one sample and the next could actually be quite small. Now, that's where it starts to get really interesting. So, you thought you were done with text, but not quite yet. So we saw that with ASCII, or with, say, 8-bit ASCII anyway, whatever extended ASCII, you need 8 bits for each single character. And that's called a fixed length code. Every single character takes the same number of bits. Now we did see obviously that with Unicode, it can get a bit more complicated, and it was variable. But if we're in plain vanilla ASCII land or an extended ASCII land, you get 8 bits, that's a character, another 8 bits, that's a character, another 8 bits, that's a character. Now, you'll recall I asked you to take a look at a particular video in time for class, and I asked you to play Hangman. Do I have a marker? I don't think I do. Nope, so we missed the point there. And when you're playing Hangman, when you say like, okay, there's a number of letters in this movie or in this book title, what's your first guess? No one starts with Q. No one goes straight for the Z. People go, for the E, the T, A, O, N, R. They're all good guesses. And why are they good guesses? Come on, lads. Well, first of all, there's a vowel pretty much in everything. If you do A, E, I, O, and U, you've pretty much, got some hits there, where there isn't a Z in everything. In general, some characters in English occur much more frequently than others. That's why, for example, if you do a substitution cipher where you just change, where instead of wherever there's a T, I'm going to put a Q, and wherever there's a P, I'm going to put an X, why they don't work very well, because just looking at the frequencies of the letters, you could actually tell, well, that's probably standing for T, that's probably standing for E, and whatever. So, in all languages, some characters occur more frequently than others. And in English, T and E, for example, occur very frequently. That's why, for example, in Scrabble, some letters earn more points than others. If you can make a word with a Q, you get more points, because that's not as easy to do. And Samuel Morse, when he was devising Morse code, he twigged this, that it would be more efficient if the more frequently occurring letters had shorter codes than the longer ones. So if you look at Morse code, the letters don't have the same number of dots and dashes. In order to figure out the frequencies, it's not like he could write a program, throw in a few novels and, get some Perl script to count up all the letters. So he went along to printers and had a look at their type trays. And he saw, for example, that most printers would have a lot of T's, a lot of E's, a lot of A's, and they didn't need as many Q's and as many X's. And so he used the number of letters a printer needs to print a document as a proxy for the frequencies. It turns out, if we're not going to look at Morse code, but it's tempting to think that Morse code with its dots and dashes might be sort of a proto-binary code, might be one of the earliest binary codes, but actually no, because the spaces between the letters in Morse code actually count for something. So you have dots and dashes and pauses between words. So it's not binary in the way that Braille actually was. Okay, so imagine we had a situation where really commonly occurring characters like, say, A had short codes, and infrequently occurring characters like Q had long codes. Well, if you were to write down, if you were to transmit A, B, C, D, E, F, G, H, I, J, K, L, M, N, P, the whole alphabet, you probably wouldn't save anything, because you're only robbing Peter to pay Paul. For this to work, if you're saving bits on an A, then you have to be wasting bits on a Q. So a Q would be much longer, or a Z would be, an X would be much longer, and an A might be shorter. But if every time you use the letter A, you save something, and every time you use the letter Q, you lose something, you gain overall because you use the A's much more often. And so the idea here is that frequently occurring characters get very short codes, and infrequently occurring characters get really long ones. So instead of everything being 8 bits, it might be long, some might be long, some might be short. And that's quite clever. I mean, if you were to take a book and use variable length codes, you might get it down to something like 1/3 of its size without sacrificing anything. So variable length codes are quite powerful just because the frequencies are so different. If there was a language where all of the characters occurred equally frequently, then you wouldn't achieve as much. So again, we have a situation where there are properties of the data that make it susceptible to compression by one means or another. So if, for example, we had a language that had A, B, D, E, P, Q, T, and Z, with 8 symbols in this language, we would need 3 bits to represent each one. But let us further suppose that in this language, the A and E occur more frequently than, say, the Z and the Q, which isn't terribly hard to imagine given our experience of English. Well, variable length codes were known about for some time, but it was Hangman who figured out how to do it optimally. Okay. One of the problems with variable length codes is this prefix problem. So when everything is 8 bits long, you know where one character starts and another one ends. So you've got 8 bits coming in, that's the first character, okay? Another 8 bits come in, that's the next character. Another 8 bits comes in, that's the next character. When some things are only 3 bits, and some things are 4 bits, and some things are 14 bits, it can get a bit confusing. You have to know when one ends and one starts. So you must make sure that no bit sequence is a prefix of another sequence. We see that in phone numbers, right? imagine if your phone number was 9991207. And so your granny's calling you and she's a bit slow on the phone and she goes like 9 and then 9 and then 9 again, and then she pauses a little bit and she's like, you know, doing the 1. But by the time she hits the 1, you know, the ambulance could be out the door after her house. Okay? That's why nobody's phone number starts with 999, nor 112 for that matter. Okay? Because if people's phone numbers could start with 999, then how do you know someone is actually calling 999? Are they just the start of this other number? So when you have a variable length code, no short code is the beginning of a longer one. So if you get 101 and that's the code for A, then no other thing is allowed to start with 101. You can't have like a 10101 meaning P. Because when you see, after you see the 101, well, how do you know? Is that the end of the A or the start of the P? Well, the answer is you don't know. You can't know. So you have to organize your code in such a way that that never happens. So we typically devise a tree where we would lay out the bit sequences in a tree, and then there's no danger of that. And for every very, very short code you have, you're ruling out future possibilities. So if you, for example, have for E, in your document, E occurs so frequently, you decide that's just going to be just 0. So just a 0 on its own, that's E. Well, now you've already ruled out half of the possible bit sequences from here to infinity. Now, okay, you still have infinity, but you know, it's half infinity. It means then that some sequences are going to be much, much longer. So although you're robbing Peter to pay Paul, overall you save, because the frequently occurring ones use a lot less. Okay? So, Huffman was a postgrad, University of California at Santa Cruz, I think, but maybe somewhere else. And at that time, people knew about variable length codes. And what they would do is they would look at the data and they would try to come up with a good variable length code. His lecturer set as an assignment, you know, to devise an algorithm for doing that, and he figured out how to do it in a way that was optimal. So that's why we call it Huffman coding. So while he didn't figure out variable length codes, he figured out how to devise them. And so that's one of the main compression algorithms we have. Now, of course, the interesting thing about computer science is that, you know, these things didn't happen 200 years ago. I mean, you could have bumped into him in the pub, you know, up to not so long ago. He died in 1999, 2000, I think. Not sure. So it's also great inspiration to lecturers to set students impossible, unknown tasks, because they may actually discover them. Okay, so this is very well documented, how you actually do this algorithm. So you can find out about that on the web, and I put that movie online that explains how to do that as well. So you start by counting up the frequencies, and that's an important point. You do need to know in advance what the frequencies are. So if you have a book stored, you can analyze the book, see which letters occur more frequently than others. You have your frequency table, and then you can do your Huffman coding and store it or transmit it efficiently. If you don't know what's in the book, that can be a bit of a problem. So Huffman coding works when all of the message or all of the document is known in advance. So you scan through it and analyze it and use the information you get from that to do your business. If it's just a message coming character by character, well, that doesn't work then. You don't have it in advance. Okay? So there's more of that there. I propose that you look at that again, since I'm sure you all looked at it already, having been asked to. So if you want to look at that again, the main thing this algorithm does, well, the thing that it does is it lines up all of the symbols by frequency and then merges the two smallest subtrees together, and that combined subtree has a weighting based on the sum of the frequencies. And so you line them up again in order of frequency, always merging the two smallest ones. So here we have 6, 6, 8, 10, 10, 60. We'll merge the two 6s to give us a 12. Now, when we sort those by weighting, the 8, 10, 10 are smaller than the 12. So now we would merge the 8 and the 10 together to give a weighting of 18. When we sort those, we'll have 10, 12, 18, 60. The 10 and the 12 will get merged, give us 22. We'll end up with an 18, a 22, and a 60. The 18 and the 22 will merge together with a 40 and 60. And finally, we have our tree built. Now here I made them all add up to 100. So you might be looking at percentages or you might be looking at absolute values. Either way, it should add up to the total. So once we have that tree, then you'll notice that the infrequently occurring characters are down at the bottom. They're the hardest ones to get to. And the frequently occurring characters are up at the top. And the path from the root of the tree down to one of the branches will be shorter for the frequently occurring characters, and it'll be longer for the infrequently occurring characters. And so if we decide that the left-hand side is 0 and the right-hand side is 1, then we end up then with our codes for each of our characters. So there, an A would be 0, 0, 1, because we follow it from here, 0, 0, 1. Whereas a D would be 0, 1, 1, 0, 0, 1. You'll notice that because of this tree structure, the prefixes are never a problem. It's impossible to encounter the prefix issue here when it's devised as a tree. Okay? So for those of you that have done a lot of programming, this is one of the favorite assignments lecturers give to do with like linked lists and navigating through trees and things like that. So you can take a look at that video and hopefully it explains it well, and if it doesn't, I can answer some questions. But I won't go into the detail of that. You can take your time with the video.